Hello and welcome to our lesson on metals in displacement reactions. So in our previous lesson we looked at copper and we looked at separating copper using carbon, which is up here in a displacement reaction, and we could do this in the lab because it required relatively little energy. So my question is, what about the heat energy needed to extract iron? Do you think we could do this in the lab? Well, we don't do this in the lab, and hopefully you would recognise the reason for that is because it's higher up in the reactivity series. The iron would require more heat energy to displace it using the carbon, and that's not something that we can do in the lab. So on an industrial scale, you're talking about a blast furnace and several other processes going on here at the same time. But the basic reaction that goes on that you guys need to know about is very simply that displacement reaction you can see in the green box. So I've got iron oxide and carbon making iron plus carbon dioxide. So the carbon has displaced the iron because it's more reactive, and the iron has been left on its own, which is exactly what we need, because then we can process that iron and make it into something useful. So if we look at what's actually happening in the blast furnace, we have our rock here, the ore, the iron ore, with the iron and the oxygen, and we have the carbon here. So sometimes it's called carbon, sometimes they call it charcoal, sometimes they call it coke, which is basically they heat up coal to make it more carbon rich, but it's all basically carbon. It's the carbon they're looking for, and they heat it up. We need the activation energy to get this reaction going. Irons, it is reactive, more reactive than copper, but it's still not that reactive. So we get a lot of activation energy. We heat it up to high temperatures, lots of energy, and the carbon is able to displace, take the place of the iron, and the iron is left on its own, which is perfect. That's what we want. Now you might notice then that the iron lost its oxygen, didn't it? In which case we would say that the iron is reduced, okay? It's lost its oxygen. And so this is a reduction reaction. But we also said that the iron was displaced by the carbon. So this is also a displacement reaction. The carbon itself is gaining oxygen, and so it's oxidized. This is an oxidation reaction. So displacement reactions will also involve oxidation of something and reduction of something, and those two always go together, because if something's losing oxygen, something else has to be gaining oxygen, because that oxygen doesn't just disappear. So they always work kind of hand in hand. For higher guys, you then do half equations and such, and you need to make sure you're okay with them. There are other lessons on that in previous units. So the core concept here in displacement, a more reactive element will displace a less reactive element. And the reason I've said element, not metal, is because when we looked at the halogens in Unit 4, we looked at the halogens which are non-metals, and they were displacing other halogens. So because one was more reactive than the other. So it's the more reactive element, whatever that is, metal or non-metal, displacing the less reactive element. So this might be quite difficult because you probably don't have a reactivity series in front of you, but hopefully you could have a go. So if you want to pause the video, have a go. If not, I will continue. So the first one here, magnesium oxide plus sodium. I know sodium is more reactive than magnesium, and therefore this will work. This is going to be a displacement reaction where I have sodium oxide plus the magnesium. Notice I had magnesium, oxygen and sodium at the beginning, and I still have magnesium, oxygen and sodium at the end, but they have rearranged themselves because I have to make something new. Okay, so the next one then, I've got iron sulfide plus zinc. Zinc is more reactive, so it is able to displace, so I would end up with zinc sulfide plus iron. Next one here, copper chloride plus calcium. Calcium is definitely more reactive than copper, so I'm going to have calcium chloride plus copper. Sodium oxide plus potassium. Potassium is more reactive than the sodium, so I'm going to get potassium oxide plus sodium. This one here, I've got magnesium nitride plus iron. Now, magnesium is more reactive than iron, and that means that the iron is not able to displace the magnesium, because the magnesium is the more reactive one. It will hang on to the nitride, and the iron is not able to do anything about it. And so you could just put no reaction, or you could simply just write out the same again. This is actually not a chemical reaction because I haven't made anything new. And finally, calcium carbonate plus sodium. Sodium is more reactive than calcium, so I'd end up with sodium carbonate plus calcium. Okay, so if you're up to a challenge, have a look at this extension. How could you investigate how reactive lead is compared to iron and copper? So if you imagine you're in the lab and you've got these three metals, lead, iron and copper, you would also need some compounds, something like lead sulfide, iron sulfide and copper sulfide. You'd need a compound form of them as well. And the question is, how would you know, or how would you investigate which one's more reactive? Okay, so pause the video and have a go. This is quite an involved one, so have a think and see what you can come up with. Okay, so what answers have I got? Well, this is quite lengthy, but hopefully it will kind of explain to you the thought process behind it. So first of all, I would need to carry out an investigation using the metal element, so that's lead, iron, copper, and the metal compound, e.g. iron sulfate, copper sulfate, and lead sulfate. So react each metal with each metal compound and observe any reaction. So I'm going to react lead with iron sulfate, lead with copper sulfate, lead with lead sulfate, and then do the same for the iron and the same for the copper. I'm going to observe if there's any reaction, because that would be displacement reaction. If there's a reaction, the element was more reactive than the metal in the compound. So for example, if I do lead plus iron sulfate and I have a reaction, the lead has been able to displace the iron from the iron sulfate. However, if there's not a reaction, the metal in the compound was the more reactive one. So again, if it was lead plus iron sulfate and there's no reaction, the iron must be the more reactive one because it's not being displaced. And I would use these results to create some sort of order of reactivity. So this sort of question sometimes comes up, so have a go at this one for me. Copper sulfate is a blue solution. Predict what you think you would see when you add an iron nail and leave it for a while. Give a reason for your prediction. So pause the video again and see what you can come up with. Okay, so the key for me here is it says copper sulfate is a blue solution. It may not tell you that because you really do need to know that copper sulfate is the blue solution. It's the one that we use all the time. It should really be knowledge in your head by now. But let's have a look. So what have I said? I've said that copper is less reactive than iron. I knew that. Therefore, iron will displace the copper. So it will become iron sulfate and copper. So I'm showing that reaction. I haven't written down the reaction there. That would have been a good thing to write down, wouldn't it? Either the word equation or the symbol equation. Well, if I'm making iron sulfate, I would see a colour change as the copper sulfate, which is blue, becomes iron sulfate, which isn't blue. So my liquid would change colour. But what about where would the copper go? Well, I would actually see solid copper forming either at the bottom of the liquid or around the layer of the iron nail as it's attracted to the metal itself. So I would see copper forming in a layer on the iron nail. So if you didn't get there yourself, hopefully you can see the logic there. Copper sulfate is blue, so as it becomes less copper sulfate and more iron sulfate, it gets less and less blue over time until actually it becomes clear. Okay, so I want to look at a little bit more at oxidation and reduction reactions in detail. Now there is a split between foundation and higher, so I'll try to make it really clear which bit foundation needs to be doing and which bit higher needs to be doing, but you both need to stick with me, okay? So first of all, foundation. Foundation, guys, you need to know that oxidation means something is gaining oxygen. So if you look at the reaction in the green box, which element didn't have oxygen at the beginning but does have oxygen in the end? Which one has gained oxygen? Well, hopefully foundation, you would recognise that carbon started on its own and by the end it's got oxygen, so the carbon has been oxidised to carbon dioxide. Higher, guys, you need to remember that oxidation is the loss of electrons. So what's actually happening here, when you go from the carbon atom to the carbon compound, now technically it's a covalent bond, so it's sharing, but it's kind of lost those electrons and given them or sharing them with the oxygen. And you'd need to, this is the bit where you remember oil rig. So this is the oil bit. Oxidation is loss of electrons. Okay, so what about reduction reactions? Well, foundation guys, you need to know that reduction is losing oxygen. So which element started with oxygen but by the end doesn't have any? Well, hopefully you would recognise that the iron here started with oxygen, but by the end it's on its own. So you say the iron oxide has been reduced. Higher guys, you need to know that reduction is gaining electrons. So we started off with an ion of iron, and it becomes an iron atom. Okay, and how does it go from the +2 to a neutral charge? Well, you have gained 2 electrons, so that's a reduction reaction. Okay, so you've got those 2 extra electrons as well. And you would remember reduction is gain. Now, you would need to know how to do the half equation for this, but again, there is another video on that, so I'm not going to go into it here. So foundation guys, your core concept, I apologise it's not written down, is oxidation is gaining oxygen, reduction is losing oxygen. And higher guys, you need to remember oil rig, oxidation is loss of electrons, reduction is gain of electrons. Okay, I give up, I can't help it. I'm going to look at half equations again guys. So there is another video, but I'm going to look specifically at displacement reactions with you right here in case you have forgotten. Foundation guys, you are finished, you may stop the video. Okay, I'm going to get rid of carbon because carbon's difficult to work with because it's a non-metal. So I'm going to change it to zinc and zinc oxide here, but it's the same idea. Okay, it just makes it a lot easier to work with. So I want to look at the iron first. So iron oxide, or the iron in iron oxide, is an ion with a charge, a +2 charge. Okay, if in doubt the transition metals, just go for +2 because you're 9 times out of 10 going to be right. In fact, probably 10 out of 10 times going to be right. So Fe 2+. And by the end of the reaction, you're ending up with iron atom, okay, with 0 charge. And so how do you get from a 2+ to a neutral charge? You are going to add 2 negative electrons. So this is, if we're adding or gaining electrons, this is reduction. So the iron oxide is reduced. And how would you write that? You would write it something like this. So you start off with the ion, I'm adding 2 electrons and I'm making the atom. Okay, and I would just, work your way through it. Is that what I'm doing? Where do I start? Where do I finish? And how do I get there? Sometimes in the exam they write it the other way around. So the Fe2+ is, it's kind of the same, they're equivalent to the atom taking away these 2 electrons. So if you're writing it yourself, you can write it either way. It doesn't matter if you get the mark, but just be aware sometimes they write it themselves the other way, and it's just a different way of doing it. So obviously that was only the half equation. The other half of the equation then is looking at the zinc. So in the beginning and the reactants, the zinc was an atom, it had a neutral charge, and it makes zinc oxide, so it becomes the ion, it becomes the +2. So how do I go from an atom to an ion? Well, I am losing electrons. So in this example, I'm losing electrons, so it's oxidation, and it would look something like this. So Zn taking away the 2 electrons and giving you the ion. They don't write it another way in the exam for this one, so it's just the other one. It doesn't matter which way around it's correct. Okay, why don't you pause the video and have a go at the 2 half equations for this reaction. Okay, so I'm going to start with the zinc, so it should look something like this. So the zinc was an ion and it becomes an atom, and zinc is reduced, and then the potassium is oxidized because it has gained electrons in that process. Okay, so pause the video and have a go yourself. Okay, so I'm going to start with the copper. I would always have oil rig written down just to check myself because I get muddled up so very easily. I've got an ion into an atom, I'm gaining electrons, so it's reduction. And then with the iron, I am losing electrons, so it's oxidation. Okay, so pause the video and have a go at this question for me. So first of all, then, does the half equation show reduction or oxidation? So I'm looking at the half equation and it's gaining electrons, and so it's showing reduction. And second of all, it says a full balanced symbol equation for the conversion of zinc sulfide to zinc oxide and sulfur dioxide. So you're just doing the balanced equation there. Okay, that's it for this lesson, guys. I'll see you later.